Today, I'd like to speak to you about three common misconceptions about minimum ventilation. The first is one of the primary purposes of minimum ventilation is to supply young chicks with oxygen. The fact is, minimum ventilation has essentially nothing to do with oxygen. The fresh air requirements to supply 25,000 day old chicks is approximately 15 cubic meters per hour, which can be easily supplied using a 7 centimeter computer fan operating only 10% of the time. Even for 25,000 market age broilers, we only need to bring in around 2,500 cubic meters per hour of fresh air to meet their oxygen demand, which only requires the use of a 30 centimeter exhaust fan. The fact is, even the effect of CO2 on broilers is often overstated. There was research conducted in 2008 at the USDA lab at Mississippi State. They continuously expose birds to 3,000, 6,000, or 9,000 ppm from day 0 to day 14, 24 hours a day. They examine blood chemistry, overall performance, and heart condition. They found that increasing CO2 from 0, which is ambient is more like 400 ppm, to 3,000, 6,000, or 9,000 ppm did not affect blood chemistry. Increasing it again from 0 or ambient to 3,000, 6,000, or 9,000 did not affect 28 and 98, 49-day broader weight gain or feed conversions. The thing they did find is that increasing it from ambient to 9,000 ppm 24 hours a day for 14 days slightly affected mortality due to pulmonary hypertension syndrome. So to be on the safe side, we should generally keep it below 5,000 parts per million. The fact is, it pretty much is most below that level most of the time. So is it a concern? Yes. Is it a primary concern? Not really. The fact is, cold weather ventilation, minimum ventilation, is all about managing house moisture levels. Excessive house moisture can lead to wet litter, ammonia, foot problems, and overall health issues. Insufficient house moisture can result in dust, which can increase susceptibility to disease. And furthermore, insufficient house moisture usually means you're overventilating, so you're going to have high heating costs. To control house moisture levels, we need to essentially ventilate based on the amount of water the birds are adding to the house each day. In short, whatever the birds are drinking each day, we need to remove each day. How do we determine how much we need to ventilate to remove the water the birds are adding to a house each day? Under typical wintertime conditions, and for sake of argument, we're going to call typical 27 degrees inside with a 50% humidity, outside 5 degrees C at a 50% humidity, we need to exchange approximately 100 cubic meters of air to remove 1 liter of water from a house. So if a water meter indicates that 1,000 liters flowed into a house on a given day, we need to exchange 1,000 liters times 100 cubic meters of air, multiply those together, and we need to exchange 100,000 cubic meters of air per day. Or in terms of cubic meters of air per hour, 100,000 divided by 24 hours is about 4,000 cubic meters per hour over the course of the day, which could be supplied by a 40 centimeter exhaust fan. Now, what if conditions aren't typical? How do minimum ventilation rates vary with inside and outside conditions? We developed an app to help answer that question. It's the Poultry 411 app, Minimum Ventilation Calculator. You open up the app, click on calculators. There's two different calculators, a minimum ventilation calculator and a house leakage area calculator. We click on the minimum ventilation calculator. We input our outside temperature and humidity, our inside temperature and target humidity, and the moisture removed per day, which is water consumption per day, and the air moving capacity of the fans that we're going to use for minimum ventilation. Click on that, and we get our answer. So let's look at an example. Let's say we have 14-day-old broilers, It's 27 degrees inside, and our target humidity is 50%, which is pretty much what ideally we'd like to have. Outside, it is 5 degrees C with a humidity of 50%. We're going to use four 8,500 cubic meter per hour, 60 centimeter exhaust fans for minimum ventilation. Our daily water consumption is 2,500 liters. We open our app. We put in our outside temperature of 5 degrees, our humidity of 50%, and the app will calculate actually how much water there is in a cubic meter of air. In this case, there's 3.2 milliliters of water in every cubic meter of air. So if we bring in 1 cubic meter of air, we are bringing in 3.2 milliliters of water. Inside, again, we're going to say it's 27 degrees C, 50% humidity. We put that into the app. For our inside conditions, what do we find out? The inside air, there's 13.4 milliliters of water in every cubic meter of air. So if we bring in or exchange 1 cubic meter of air, we're bringing in 3.2, getting rid of 13.4, which means for every cubic meter of air we exchange, we will remove 10.2 milliliters of water from the house. Next, we put in how much water we need to get rid of, which is how much water the birds are drinking, along with our minimum ventilation fan capacity. So we're going to put in 2,500 liters, and our cubic meters per hour, 4 times 8,500 is 34,000 cubic meters per hour. Hit calculate, and we come up with our answer. To get rid of that 2,500 liters of water under those conditions requires us to continuously exchange 10,213 cubic meters of air. The rule of thumb said we need to do 10,416. So you can see the rule of thumb under these conditions isn't that far off. Now, since our fans move more air than we need, we could put them on a timer. If we had on a 5-minute timer, we'd operate them 90 seconds out of 5 minutes, or 90 seconds on, or 210 off. Or on a percentage timer, we're going to run those fans 30% of the time. Of course, you could put the fans on a variable speed and slow them down and bring in that much air, but at least you have a figure of what you're trying to do. Now, though it can be used to provide a minimum ventilation estimate during a specific flock, one of the more useful ways to use the app is to explore how changing inside and outside conditions affect our minimum ventilation rate to control moisture. For instance, how would the minimum ventilation rate change on a rainy day? So instead of having our outside conditions 5 degrees C and 50% humidity, we're going to say 5 degrees C and 100% humidity. So you can see right here, we put in our 5 degrees C and 100% humidity, and it changes the amount of water that's in the outside air. Now it's 6.5 milliliters for every cubic meter of air. Before, it was 3.2. Obviously, it's 100% humidity, so the air outside has more moisture in it than it did before. And now there's less of a difference in moisture levels between inside and outside, which means our ventilation rates are going to have to increase. Before it was 10.1. For every cubic meter of air we exchange, we get rid of 10.1. Now it's only 6.9. So we're less effective in a way of pulling moisture out of the house. Our ventilation rate increases from 10,000 cubic meters per hour roughly to 15,000 cubic meters of air per hour, which is an increase of 48%. So on a 5 degrees C day, when it's raining, you have to increase your ventilation rate 50% because the air you're bringing in is more moist than it was before. It's still drier than the inside air, so we can still remove moisture from the house. How would it change if it was colder? Let's say outside is 0 degrees with 50% humidity. There you can see the amount of water in the air actually decreases because cold air can hold less moisture than warm air. We're at 2.3 milliliters per cubic meter. Before, at 55 degrees C and 50% humidity, we're at 3.2. So now for every cubic meter of air we exchange, we remove 11.1 meters of water per air. Bigger difference between inside and outside, 2.3, 13.4. Every cubic meter of air exchange, we remove more water when it's dry. We have to heat it up, of course. And our ventilation rate goes down around 10%. So the colder it gets, the less you can ventilate. The more humid it gets outside, the more you have to ventilate to keep the house dry. What if we want to change our target humidity? Let's look at different humidities. Okay, we're going to start off with 5 degrees C and 50% humidity. We've been talking about that. We know that there's 3.2 milliliters of water in every cubic meter of air. That's outside. Now inside, again, we're going to change our target. Now we're at 27 degrees C, 50% humidity. We're going to look at 40% humidity. And we're going to look at 60% humidity. If it's drier inside, that means there's going to be less of a difference between inside and outside moisture levels in every cubic meter of air, which means we're going to have to ventilate more. Less moisture in the air in the inside, less of a difference. We have to ventilate more. As opposed to 60% humidity, there's more moisture in the air inside, so there's a bigger difference between inside and outside, which means we ventilate less. We do the calculations, or the app does the calculations. At 40% humidity versus 50, we go from 10,000 cubic meters per hour to 13,000 cubic meters. We have to ventilate more now to maintain that level of 40%. In fact, we have to ventilate 36% more. 60% humidity, we can actually ventilate less. We can ventilate about 22% less. Now, what effect is that going to have on our heating costs? The fact is, since in most of our houses, our ventilation is responsible for 80% of our heating costs, you can see, hey, if we maintain a lower humidity, we have to ventilate more to do that, which means 36% more ventilation, that's 30% more heating cost. On the flip side, if we let more moisture in the house, we ventilate less, and therefore our heating costs are lower. But again, we're going to have a higher humidity, which means we're more likely to get damp litter. But you can look at that. You can use the app to explore how different temperatures and humidities affect the theoretical minimum ventilation rate. And that's the important point. That's the theoretical minimum ventilation. So the app only really provides a rough estimate. How much air we actually need to remove a given amount of water the birds are adding will vary with house tightness. The tighter the house, the more air comes through the inlets, the more effective we are at removing moisture. But if the house is loose and it all comes through cracks, you actually have to ventilate more because you're less effective at conditioning and drying that incoming air. Stratification, if all the warm air is sitting next to the ceiling, that's where the dry air is. And if the cool air is at the floor, we have to actually ventilate less because the cool air is less effective at removing moisture from the litter. Inlet performance, again, the more air that comes through the inlets, the better they throw the air, the better they heat up that air, the better they dry it out, the less air we have to bring in. Of course, temperature and humidity changes over the course of the day. You don't want to constantly keep on recalculating how much you need to do. The app gives you a starting point, but it will change over the course of the day with changing outside temperature, humidity, level of the air movement. The more air movement we have in the house, the easier it is to pull moisture out of the litter, which would affect our ventilation rates, water meter accuracy, of course, how accurate is that, etc. So the best way to determine the correct minimum ventilation rate to control house moisture is to use the minimum ventilation app as a rough starting point, then adjust that rate based on the current relative humidity. The target humidity is typically between 40 and 60%. If it's above 60%, you're probably ventilating too little. If it's below 40%, you're probably ventilating too much. You're removing too much moisture from the house. Here's an example of incorrect minimum ventilation. You can see over the first 10 days of the flock, the relative humidity is increasing, which means each day the birds are adding more moisture than you are removing. But if the humidity is more constant over the first 14 days or the course of the flock, that means moisture added equals moisture removed. You're in a steady state situation where you're removing what the birds are adding, so air quality will be constant, litter moisture will be constant, and bird health will be more likely a constant. Another common misconception I hear is people say, "Oh, my houses are pretty tight." But are they? You just look at a house. How do you know if the house is tight? You might think, well, there's no giant holes in the wall. That doesn't mean that it's tight. It means that it's not really, really loose. So to come up with a way to quantify house tightness, again, we have a poultry house tightness app. It's the same Poultry 411 app. We click on calculators, but this time we click on house leakage area calculator. A new little page comes up where you put in your house length, the fan capacity you're using to determine your house tightness, which I'll touch on in a moment, and the static pressure measured. Now, the best way to show how this app works is to go through an example. Let's say we have a 12-meter by 100-meter broiler house, and everything is closed tight. There's no birds in the house. We're just going to close up all the inlets and make sure the in-wall doors are closed and everything's nice and tight. So we use our app. We're going to put in a length of 100 meters, our width of 12 meters. Now we're going to turn on a couple fans and measure the resulting pressure. The higher the pressure, the tighter the house. But how much fan capacity should we turn on? I generally use as a rough estimate. It doesn't have to be exactly. It's going to be plus or minus 30%. 1 CFM per square feet of floor space and exhaust fan capacity, or in metric, 20 cubic meters per hour per square meter of floor space. So in this example, what I'm going to use is 17,000 cubic meters per hour, which would be two roughly 60 centimeter fans. So that's the fans I'm using. And let's say, okay, I got 50 pascals of pressure. That's what my gauge measures with. Everything closed up tight. What does that mean? We put those numbers in, hit calculate, and we come up with some numbers. On the next page, first thing it says is total house leakage area. Now, in this example, it says 0. It's actually 0.4. I'm currently having this app modified to show decimal places, so bear with me on that. That is actually 0.4. Now, that's how many square feet of leakage is scattered throughout the house. But what does that mean? Well, first we can put it in relative terms. How much leakage there is for every 1,000 square meters of floor space. So you can compare houses of different size using that number. Okay, but what does that number mean? We actually have a scale going from perfect to very poor. In this particular case, 0.35 square meters of leakage for every 1,000 square meters of floor space actually is excellent. It's above excellent. So this is a nice, really tight house. But, okay, it's tight. How would this affect the performance of our minimum ventilation system? So there's a second part of this calculator. It's called the inlet system effectiveness calculator in a sense, which will actually show you how good your inlet system will perform during minimum ventilation for a house of this tightness. So, again, our 12 by 100 meter broiler house. Our minimum ventilation fan capacity, let's say for argument's sake, we're going to use two 60 centimeter exhaust fans for minimum ventilation. And we want to know when those two fans come on, how is our inlet system going to perform? Put that in there. The next, we have to put in the inlets we're going to use for minimum ventilation, the number of inlets, their width, and their height. So let's say we're going to use 40 inlets that are 30 centimeters by 45 centimeters. So 30 centimeters in height, 40 centimeters, 45 centimeters in width when they're wide open. And that's what we're going to use for minimum ventilation. Put those numbers in right here, hit calculate, and first thing it tells us, using those two fans, how much inlet area do they require? 0.82 square meters. So it just tells you how much opening we need to feed those two fans. The next thing it tells us, with those inlets, how much they're going to open to supply this much area. So in this case, we turn on two fans in this nice tight house, those 60 centimeter fans, and the inlets are going to open up 4.5 centimeters, which is a good opening. I'm typically looking for something in that 4 to 5 centimeter opening because I think I can get pretty decent throw with that at a 0.1 pressure, and that's what this assumes is a 0.1 or 25 pascals of pressure. Now, the real interesting thing is it tells us the percentage of the air that will enter through inlets. So in this case, they're going to open up, all of our inlets are going to open up 4.5 centimeters, And 66% of our air will enter through the inlets, 44% will enter through cracks, which is pretty good in this scenario. What happens if the house is looser? Instead of getting 50 pascals, we have a house that only got 25 pascals of pressure when we closed up everything tight. So, again, we do our leakage calculator. We come up with this. What does it tell us? We have 1 square meter of leakage area. That, remember, before is 0.4, so this house is definitely looser. Our rating is only a 0.6, which is good, but not great, not excellent. We put in our minimum ventilation fan capacity like we did before, 17,000, 40 inlets, 30 by 45 centimeters. What did we learn? Total opening required is 0.52. We need less inlet area required because the house is looser. The inlets only have to open up 2.9 centimeters, and now only 42% of our air will enter through our inlets. We're becoming less effective. Let's slow the fans down. I don't want to run those fans at full speed. I'm going to slow them down 30%. So we have a loose house with fans running at 70%. So our air moving capacity goes down to 12,000 cubic meters per hour. Hit our calculate. What do we find? Now we only need 0.15 square meters because our fans are moving less air. They're only going to open up 0.9 centimeters, and only 18% of our air will come through our inlets. All the air is basically coming through the cracks. We're not getting mixing. We're not breaking up stratification. We're not really making things better for the birds. Now, let's look at something else. Let's put in a continuous inlet. We have a looser house, slower fans, continuous inlet. Again, 12,000 cubic meters per hour. Again, number of minutes, 1. Maximum opening is 25. And we have 10,000 centimeters of it. That's the length of the house. Hit the calculate. Our inlets will only open up 0.2 centimeters, and 18% of the air will be entering through those inlets. So basically an ineffective inlet system. You can go through all the different combinations. It's not perfect, but it does give you an idea of how house tightness and the number of inlets you have and your minimum ventilation fan capacity is going to be how they all interact. The third misconception, at least in my opinion, if you have too much air speeds over 0.25 meters per second or 100 feet per minute during brooding, you will chill your chicks. Now, first, not having a well-designed circulation fan system can result in poor temperature uniformity, cool chicks, high fuel usage, and wet litter. Bottom line, you're going to end up with poor bird performance if you don't mix the air properly. Now, what do I view as a recommended circulation fan capacity? We've been doing a lot of studies over the last 3 years looking at circulation fan systems, and we've come up with some goals. A proper circulation fan system should be capable of moving 20% of the house volume each minute. Take your house volume, multiply it times 20%, and you're supposed to be able to mix that every minute. Those fans should operate continuously, and again, in our opinion, should be capable of producing air velocity at floor level of around 0.75 meters per second, which is 3 times what some people say you should have. How would I place the fans? I'm going to place them at the ceiling, along the center line of the house, blowing towards the ends of the house, parallel to the ceiling, not blowing down. The fan should be spaced roughly 30 fan diameters apart. So if I'm using a 60 centimeter fan, they should be roughly 18 meters apart. Let's look at the air circulation fan pattern. What we have is a high velocity at the ceiling along the center of the house. So high velocity in the middle and a slow return air velocity along the sidewall. So air goes down fast and comes back down the sidewalls in the opposite direction. It's like a racetrack, but in effect, you don't really have to racetrack fans. If I push air down the house in the middle, it's got to come back along the sidewalls. So it's producing good air movement across the width of the house. Let's look at an example of one of our study farms. Again, we probably have about 4 or 5 of them over the last 3 years. There were 12 meters by 150-meter broiler houses, no circulation fans versus the, quote, high volume circulation fans, which in this case was our 60-centimeter fans with about a third horsepower motor moving 10,000 cubic meters per hour. The circulation fan capacity was about 25%, which meant we mixed 25% of the house volume each minute. Average floor airspeed, which you can see in this map, which is half of the house, 40 feet by 250, which is 12 by 75 meters. Our average airspeed, we mapped it out, we found it 0.75 meters per second. Our target humidity was keep it below 60%. Let's look really quick at some temperatures. These are the temperatures at the floor and the ceiling in 12 different locations without circulation fans, with circulation fans. Much more uniform temperatures throughout the house and better utilization of the hot air next to the ceiling. We also looked at litter moisture. We looked at litter moisture in 16 locations. So we measured it near the outside drinker line and the inside drinker line of each side of the house at 4 different locations along the length of the house. So here's an example. This is our litter moisture the day before the chicks were placed. The blue are near the outside drinker line. The green are near the inside drinker line. So this is zone 1 in the house with circulation fans, labeled here as third horsepower fans. That's zone 1, 2, 3, 4. So that's all 16 locations in the house with circulation fans before we turn on the fans, before the chicks were placed. And here's the house with no circulation fans right next to it. Pretty much things were similar. We did notice on day 1, for some reason, day -1, that the house without circulation fans was actually drier than the house with circulation fans. Again, they weren't operated just for one reason. One house was damper than the other. Here we are at day 6. We start to see some differences. The litter moisture in both houses dropped to around 15%. But what was really interesting is in the house without circulation fans, that the litter near the sidewall started getting wet, which is pretty common that you see the litter getting wet in the sidewalls before it does in the middle. Whereas in the house with circulation fans, the litter moisture was uniform from wall to wall. Why is that? Well, when you look at a thermal image of the house, you can see really quickly why. In houses, and these had radiant tube heaters down the middle of the house, we tend to get an overheating of the house. Here we have, this before the chicks were placed, you can see we have a very warm area in the middle of the house. It's 105, 110 degrees, which is actually too hot for the chicks. Here's the house without circulation fans. Here's the house with circulation fans. We still have a nice floor temperature with the circulation fans, but we don't have the extreme floor temperatures commonly seen in houses with radiant tube heaters. Let's look at the birds. This is the house. The red line is the house temperature from basically 5 a.m. to 6 a.m. Here we have a time-lapse video. And the thing you see, the heaters are cycling. They're on, then they're off, then they're on, they're off. But especially during the on periods, we have these big lack of birds in the middle of the house. And that we saw, the birds tended to avoid the middle of this house, putting more chicks on the sidewall. More chicks on the sidewall meant what? More moisture being deposited into the sidewall in this house without circulation fans. Now, here's the house with circulation fans. The first thing you see really clearly, a lot more birds in the middle of the house and fewer birds on the sidewall. And the other thing you see is there's not this big cycling of temperature. Temperature's more constant. We're moving the heat off those tubes. We're utilizing the floor from wall to wall. So we're depositing moisture in the litter from wall to wall evenly, which makes it easier to control moisture. Here we see on day 10, with the house with circulation fans, moisture levels about 20%. Ideally, we want it below 25%, which we are. And in the house without the circulation fans, you can see the sidewalls are still wetter, and the average moisture level has gone up about 5%. Here we are at day 16. Still pretty uniform in the house with circulation fans, still more variation, more litter moisture in the sidewalls in the house without. And the thing we started to notice at this age was the ammonia was lower. It was 30% lower in the house with circulation fans. Why? The litter was drier. 20% versus 30%. Day 21, litter moisture, both houses went up, but the fact is it was still drier in the house with the high volume circulation fans than the house without circulation fans. Paw quality, we scored the paws. We looked at number of times throughout the flock at how their paws looked. A 0 would be no blemishes. A 1, very minor blemishes on their feet. 2 was a pretty severe blemish or blister, a bony burn. People often refer to it as on their paws there. Let's look at the paw scores and look at litter moisture. Here we are, day 16. Litter moisture of 20% versus around 30%, as I mentioned. Now, paw scores. Again, that's litter moisture, around 25% is our target. Here we have the third horsepower fans, or the house with the circulation fans. Look at very few birds showed any signs of damage. Only 5% of the birds showed some damage to their paws. Where in the house without circulation fans, 50% of the birds showed some paw damage. 10% of that was severe. Day 21, house with the circulation fans. About 10% of the birds showed some sign of damage, half of that being severe. Where the house without circulation fans, half of the birds, roughly over half of the birds showed some damage, and half of those we would consider severe damage. By day 40, big difference. We're looking at 80% of the birds in the house without circulation fans had some type of paw damage, where the house with the third horsepower fans, only about 40 or 50% of the birds showed some damage. Still higher than we want to see, but we saw a dramatic improvement. And you can see why the litter was drier throughout the 40 days in the house with air movement. Chick reaction, this was very important. We did a lot of time-lapse recording, looking at the chicks, getting reports from the grower. And we saw this time and time again on this farm as well as others, that at the right temperature, and what we saw, the right temperature is around 92 degrees, brooding day 1, the chicks didn't mind the air movement. In my opinion, air movement is only a draft if the air is cool. If the house is 30 degrees C, 29 degrees C, you move a lot of air around it, yes, the chicks will look cool. But if it's around 92 degrees, 31 degrees, 32 degrees C, the birds don't mind the air movement at all. They just scatter out. Here's another farm, a 16 by 180 meter house with 10 60 centimeter fans. Again, day-old chicks here, spread out from wall to wall. No adverse effect. We look at this house versus the house next to it, no airspeed. They look almost identical. In fact, these birds often look warmer because the floor temperatures often are a little bit higher throughout the house, especially near the sidewall. Interesting enough, we actually had a test house next to this where we had more fans. Sorry, a little point there. Which is true, that if it is warm air, it's like a tropical breeze. Not to be overly trite about it, but the fact is, do you really mind a breeze when it's warm? No. And that's what the chicks are feeling, essentially. So again, getting back to our other house next to it, this house had 20 fans in it, 60 centimeters, running full speed all the time, 24 hours a day, from the moment the chicks are placed. Look at the birds. They're all spread out. I'm not saying you need this level of fan power. We put this in just to see, would we get the birds chilled? But the fact is, at the right temperature, with the right conditions, the birds really don't mind having that level of air movement. And the higher the level of air movement, the better job we'll do at drying the litter, breaking up stratification, keeping the ammonia levels down, and keeping bird health up. So, again, it really comes down to 3 simple facts when it comes to minimum ventilation. First, we need to ventilate based off of house moisture levels. And that app will help giving you a starting point of how much you need to ventilate. And then you tweak it based on house humidity. Secondly, you need to evaluate your house tightness. And that app will do a good job of giving you a rating of how tight your house is. And you might find your house is looser than you think it is, which shows there's room for improvement to make your inlet system more effective. Last but not least, don't worry excessively about having too much air movement. With more and more pressure on keeping our litter dry, not only in the U.S., but of course Canada and other countries as well, we need to look at using circulation fans, producing more air movement over the litter to help it keep it dry, to keep our birds healthy. Thank you very much.
Well, thank you, Dr. Czarick. Very interesting to see how all those apps are helping, and the impacts that they're having on the activity and the performances in the barns. Now, we did have one question that came in already. Of course, a typical Canadian question, and maybe we'll get you just to reiterate it here. I mean, what about our zero temperatures? You had one great picture there with the deep snow on the roof, but when we get temperatures in that -40 range, is the app still effective of that, or is that something you're working on?
Yeah, that's one of those things you don't really think about until you start playing with the metric version of the app. For this presentation, I was going, oops, we can't go to zero. And I'm just emailing over the last week our app developer who's going to address that. So we'll be able to go below zero, so it'll address your climate up there. The fact is, it's good to have that, but once you start getting much below zero, there is no moisture in the air. So whether it's zero or -30, it doesn't change a lot. The bigger change is in the higher temperatures, 10s, 20s, up in there. So, but again, that's why we need it there so people can experiment and see for themselves what difference it would make.
And while we're talking here, a quick reminder, if you do have any questions for Dr. Czarick on his presentation, make sure you just throw them in the Q&A button that you see at the bottom, and we'll have an opportunity to ask him. Now, with the app, you talked about the two different kind of applications. They really sort of work together. You kind of need to do both to get that full picture of the effectiveness of it.
I think so. The first app, the minimum ventilation app, tells you, okay, how much you need to ventilate. Great. Okay, we come up with a number. But that number is theoretical because it really applies to a house that's very tight and the inlet system's working properly. That most of our air is coming through the inlets and being heated and not chilling the chicks. So the tightness app helps you to say, okay, how can I use that number most effectively? How can I make sure my inlet system works the best so I can bring in a way, as little air as possible, condition it really well. It's a lot of times with minimum ventilation, it's not quantity of air, it's the quality of air you bring in. It's like how many paper towels does it take to clean up a mess? Well, it depends how good the paper towel is. You have a lousy paper towel, it takes a lot of them. But by bringing most of the air through the inlet system, we basically turn, our lousy paper towels outside to very good paper towels, so we can actually bring in less air to control the moisture in the house.
Okay, questions are starting to roll in. One that's come in from Jerry says, a few barns have circulation fans near the side of the barn. Should they be moved to the middle if possible?
In my opinion, I like to have my circulation fans towards the middle of the house, because if I put them too close to the inlets, they disturb the airflow pattern coming out of the inlets. So if I have a good inlet system with a nice tight house and the air's throwing out to the middle, we get the air to come in fast, comes out to the middle, drops, and then the circulation fans take it the rest of the way. If I put my circulation fan near the sidewall, it actually acts as a wall, keeping the cold air from making it all the way to the middle of the house. Now, the one exception to that, you Canadians love your continuous inlets. And the problem with the continuous inlet during very cold weather, it really doesn't throw the air. So I could see the need or why people would put a circulation fan next to the inlet to help take that cool air that's just dumping on the sidewall anywhere and move it around. But that being said, in a perfect world, the circulation fan would be in the middle, move the air down to the end, and then move the warm air back along the sidewall.
Okay, we've got a couple more. Will the app work when you have air cannons?
You can put in the air cannon area. You might have to play a little bit with it. But the fact is, air cannons are really not an effective inlet system because the inlet area is just so minute. You can only bring in about 50 cubic feet per minute or about 75 cubic meters per hour through an air cannon. So the amount of air that comes through an air cannon is really minimal. Most of it's probably coming through the cracks, but technically you could, again, play with the inlet size and area and come up, just assume they're square instead of circular. And you'd see that not much air is going to come through them because there just isn't much area there to work with.
What do you like better in the winter, for usage, ceiling or sidewall inlets?
I think for minimum ventilation, I think a attic inlet definitely has a number of advantages, provided it's the right type installed, all that, because a number of reasons. A, you're pulling air out of the attic, which isn't affected by the wind. You're bringing your coolest air into the warmest area of the house, which tends to be the middle. The air tends to throw better from an attic inlet system. So in general, I would say for extreme weather, an attic inlet is probably superior. But then for moderate weather, where you're trying to start cooling the house, that's when you start looking at sidewall inlets. But again, it sort of comes into the quality of the inlet. What is the inlet? How is that attic inlet installed versus how the sidewall is installed? Because sometimes I can have a better sidewall inlet than an attic inlet. But in principle, being able to pull the air from the attic space, not being affected by wind, having just a few inlets to serve that task, I'd rather tend to go with an attic inlet.
All right, and people loved your paper towel analogy, just so you know. Another question here, what if exhaust fans are down the middle and have recirculations? Does that change mixing fan placement?
I don't think so. It's like a bathtub. I don't care where the drain is as long as everything's mixed up. There's another analogy. But I think that's, people overthink where the exhaust fan is. If the air is properly mixed, you can use a chimney fan, you can use a sidewall fan, you can use a tunnel fan, because what you're doing is exhausting well-mixed air. So to me, I could put my circulation fans, right down the middle, even next to a chimney fan. All it's going to do is help mix everything up and be more efficient. You don't want to exhaust all your hot air out of your chimneys or things like that. You want to make sure that you're exhausting a well-mixed sample of the entire house in the air.
Just while we wait to see if more questions come in, would you think a lot of producers may be surprised about how much air they're losing through the cracks? Do you think that using that tightness aspect of the app would maybe surprise a lot of people just to realize how much is escaping through the cracks?
I think most people do overestimate their house tightness, mainly because people never measure it. It's great to say, hey, I got a tight house, if you don't measure it. At least the app does sort of take the guesswork out of it. You use it, here's the number. You can compare your number to your neighbors and start talking about it. Because I'd imagine the tightness standard for Canada a lot of times is going to be a little bit higher than it would be for the US, considering your heating cost and things like that. But, if you get a rating of excellent, that's a good house. But, if you're average in your climate, you could see how that could be very costly, both in terms of energy usage and bird performance.
All right, Jerry's back with his second question. What about a low ceiling barn, not vaulted? Would it be necessary to reduce the circulation fan speed, variable speed, if it was in the middle of the barn?
Very good question. The whole part with circulation fans is that they're size relative to the house volume. So if I had a very tall ceiling and I want to mix 20% of the volume, let's say the ceiling is 4 meters in the middle, I might 4 or 5 meters. I could use a 36-inch mixing fan. We do that in turkey houses. But the lower the ceiling, what we tend to do is decrease the fan size. So on a barn that has a, 2.8 meter sidewall, 8-foot sidewall, something like that, we probably wouldn't use a 24-inch fan. They'd probably be down to a 16 or 18-inch fan. The problem I have with variable speeds, though I see their advantage, the problem is people tend to slow them down so much that the fans don't work together as a system. You want the fans, I put in 6, 8 fans. I want one fan to move the air to the next, get a recirculation and mix the whole volume. So yes, the lower ceiling, we would tend to use in a perfect world, I'd tend to use a smaller fan running at full speed as opposed to a bigger fan slowed down, but you do need less fan capacity, circulation fan capacity. That 20%, is a universal figure.
Okay, I'm going to do one last call for questions, but I do have one more in, but I'm just going to do last call. If anyone else has a question for Dr. Mike, make sure you send it quick. And Mike is back and he has a question. What are the pros and cons on tunnel ventilation in the winter? Can it work?
Tunnel ventilation is a combination of a tunnel fan with a tunnel inlet. So you have fan on one end, inlets on the other. That's tunnel inlet. That's tunnel ventilation. That will not work in cold weather. Using tunnel fans with sidewall inlets is inlet ventilation with a fan that happens to be in the end wall. And that works just fine. So tunnel ventilation is defined more in a way by the inlet location than the fan location. So if you try to use a tunnel fan with one big opening on the end, even if it's open a little and it's cold outside, it's going to be a disaster. You're going to have a cold end and a warm, humid end. But if I could use that same fan, use my sidewall inlets, pull in air uniformly down the length of the house, and it can work just fine.
And we did get one last question sneak in here for you, Dr. Czarick. Should mixing fans shoot straight out or should it fan out?
When I'm putting a circulation fan, I'm going to put it straight right next to the ceiling, blowing flat to the ceiling, not blowing down or blowing horizontal to the ceiling in a straight jet. I'm trying to move air from one fan to the next fan to the next fan. I don't want it moving around. I don't go up and down. I'm trying to create a whole house mixing pattern. You can sort of get that synergistic effect that you have 8 fans, but they'll act like 12 because they're all working together to mix the entire house volume.
All right, well, that's a good point.